Okay, so today we want to look at two problems where we want to find the equivalent resistance. And in the last video we talked about what to do when we have resistors in series and what to do when we have them in parallel. So now we have everything together. So we have a 10 ohm in series with 3 resistors in parallel that are in series with a 20 ohm. And to express the equivalent resistance, we want to express this as one resistor if possible. So the first thing we can do is look at the resistors in parallel. So from the last video, we know that we have an equation for how to calculate this. And plugging everything in, we see that we are approximately equal to 0.55 ohms. So now we can express the original circuit as 3 resistors in series, where we have a 10 ohm, a 0.55 ohm, and then a 20 ohm resistor. Now in series, we know we can just add these resistors together, so we can make this one resistor that is equal to the sum of all these, which is equal to 30.55 ohms, and that is equal to our equivalent resistance. Moving on to the second question, we have something similar, but it's also very different. Again, we want to find the equivalent resistance. So we see that we have a 1K resistor in series with this network. So if we look at the network first, we know that we have this. Where this is our 2K, this is our 10K, here's our 5K, and here's our 2K. So I dropped the ohm symbol from this. Many people will. Usually you'll see resistors either in K or M, but the ohm is always there. It's quicker to write it this way, and everyone gets the hang of this right away. So we know that we have 2 resistors in series right here, so we can call this a 7K resistor. Now using the same formula, we can find out what that resistance is, which is equal to 1.346 kilo ohms, just for the network to the right of the 1K. So now we can rewrite our circuit as this, where we have a 1K and 1.346K. We know that we can add these because they're in series, which leaves us with a single resistor that is 2.346 kilo ohms, and that is our equivalent resistance. So now we can look at an extra part that always helped me out in undergrad. So we want to consider 2 resistors in parallel, R1 and R2, and we want to know if the equivalent resistance can ever be greater than R1. So we'll keep it symbolic for now. You'll see why later. So we can set up that inequality. We know what the equivalent resistance is for 2 resistors in parallel. And we will put our greater sign with a question mark in R1. So we want to try to test this. So first we can divide by R1, which gives us R2 over R1 plus R2. Is that greater than 1? We can go one step further and simplify this by factoring the R2 out of the numerator and denominator into this. And this is as far as we really need to factor it before we can think about it. So we know that R1 and R2 are positive values. So we have 1 over something slightly bigger than 1. Is that greater than 1? Well, it shouldn't be, and you can test it with any value you want. So what does this really say? That the equivalent resistance is always smaller than R1. And that is true. Another case we can look at is, what if R1 is equal to 0 ohms? Well, given the equivalent resistance formula, we know that the equivalent resistance is equal to 0 ohms. So we know that R equivalent is always less or equal to R1. And the equal sign comes in with the very special case of a short circuit. So what does this say in the end? It says your equivalent resistance is smaller than R1, but we can plug in any value for R1. We can make R1 our smallest resistor in the parallel resistance. And this works for any amount of resistors in parallel. So the golden rule to take away is R equivalent for resistors in parallel is always smaller or equal to the smallest resistance in all of the resistors. So, with that being said, we can end it here.